Just as a little bit of a preamble, first of all, thank you all for coming tonight to a virtual lecture from our friends over at PAE Engineers. David and Alper will be talking today about whole life carbon, and I am just as interested in what that actually means as you are. This is the last in a series of lectures sponsored by Loney Architecture that have two purposes. One was to make us all better at creating zero net carbon buildings, and also to fulfill all of our learning credits. So if you haven't yet, you will get your 1.5 hours of zero net carbon learning credits for this that are good not only for your AIA, but also for your license renewal. So that's what I got to say about that. So without further ado, I would like to introduce our lecturers this evening, David and Alper. Thank you, gentlemen. Take it away.
Thank you, Mark. David, would you like to share your screen, or should I just go ahead?
Yeah, I'll share.
Okay. Thanks, Mark. And hi, everyone. I don't know if you remember me. I had given an yes, we can. So I had given earlier last year a presentation on the energy codes, California energy codes, and then today we'll be presenting about whole life carbon with my colleague David. Just to give you a quick overview of who we are. Both David and I work for the regenerative design group of PAE Consulting Engineers. We are an MEP and lighting consulting firm located in San Francisco and LA, and then we also have offices in Portland and Seattle and 2 other locations on the West Coast. And in terms of our experience, we worked in various living building projects. There, if you can move on to the next slide. Sorry, yeah. So I mean, as a firm, we help solve the planet energy and water challenges. So we always have a emphasis on the environment impact when we are considering different design solutions in all our projects. And yeah, obviously the whole life carbon is an important aspect of that, which we'll be going into further detail today. And in terms of our project experience, we have worked on several living building projects. 5 of those are built and achieved certification, and then we have 12 more pursuing it. And then we have 12 carbon neutral projects, 44 net zero energy projects, and various passive house and LEED platinum and all electric buildings. In terms of the building types that we work on, so it's a wide variety ranging from residential, single family, multifamily to commercial, cultural and government, as well as higher education. So again, today's scope will be applicable to all different building types. And then yeah, our services, as I mentioned, we do mechanical, electrical, plumbing design, as well as technology, commissioning, and architectural lighting design. And then finally, regenerative design group, which is our building performance analysis, as well as carbon GHG consulting, design and analysis of renewable energy systems, as well as sustainable district planning. And the next one. So yeah, Mark already mentioned today's session is an AIA accredited session with the learning objectives as listed here. So today's lecture will help you identify the key concepts in embodied and whole life carbon metrics, describe international efforts to implement whole life carbon regulations, explore how whole life carbon can transform project performance, and apply whole life carbon analysis to case studies. So I would like to start with, we're talking about whole life carbon. You're hearing a lot more about it recently. Part of the reason is because in addition to the interest and the recognition in terms of the environmental impact, we have a bunch of regulations in California that are slowly becoming effective. Starting with the Buy Clean California Act. This was an act that was passed back in 2017, and it required, initially it required all the contractor teams working in state projects to declare environmental impact sheets for certain material types like concrete and steel and insulation. And it was used to create a database, materials database for the state of California. So this act was passed in 2017, right? And then later, last year in 2022, the Carbon Intensity of Construction and Building Materials Act has passed. And then this act basically requires a framework to be established by the end of 2025 in California, which has certain goals that I'll get into detail in the next slide. And lastly, as an extension of this act, and AIA was involved in this effort too, as you probably already know, now we will have embodied carbon limits on all new construction projects by starting or becoming effective in July 2024. And I'll get into a bit more detail in the next slide on that one as well. So the Carbon Intensity and Construction Building Materials Act, it requires a carbon framework to be set or established by July 2025. And there will be a baseline established for this framework by 2026. And then the target or the goal of this framework will be the reduction of GHG emissions of materials by 20% by the year 2030. And then the next target is a 40% reduction of the building material related emissions by 2035. And as an extension of this effort, we are seeing more regulations as a part of the Cal Green, which is the building code in California, as you know. So this regulation this requirement was recently passed, and it will become effective in July 2024. And it requires all new non-residential commercial buildings over 100,000 square foot and all school buildings that are over 50,000 square foot to comply with a certain embodied carbon pathway. So for existing buildings, the projects can choose to reuse at least 45% of existing structure and the exterior of the buildings. And then for the new buildings, they will either have the option to comply with prescriptive requirements for each material class in the building, or they will have the option to do a life cycle carbon analysis for these buildings and show a overall carbon emissions compliance that way. And then the intent is, so this is the current target, and then only certain size of buildings are subject to that. But by 2026, instead of 100,000 square foot limit, that will be reduced to 50,000 square foot. And then so over the years, the scope of the application of this requirement will expand further and further until it applies to most of the buildings. And we don't have like a detailed the details of these regulations yet. We're still waiting to see the draft, but we'll definitely find out more as it becomes available. And with that, I'll pass it on to David.
Great, thanks, Oper. So first question for everybody, do you believe we need to solve the climate crisis in one generation? This is something that we've been asking ourselves quite a bit in our practice. And it just kind of changes it a little bit. You see the numbers, in terms of different dates and things, but when you kind of apply it to your own practice, it makes you ask some different questions. And that's one of the goals today, is to kind of help ask some questions and help expand things so that you might think about things differently. And if anybody has questions during this, happy to field it as we go. There's only 25 people on here so far, so I don't think it'll get too overwhelming if we want to field questions as we go. So we're at this like interesting point in history of architecture and building industry that we have a couple different pathways we can go down, and we've got a journey that we're on. One pathway is towards kind of business as usual, higher emissions, and the other is to try to get to net zero carbon. And because of that net zero carbon goal, it's driving all kinds of changes through how we measure performance, which then also changes how we talk about buildings, how we think about buildings, and how they interact with the broader industries. So to date, most of the building industry has been focused on capital. So, what's the capital cost of construction and what's the operational costs of running a building? So early versions of LEED, that's the main focus that was as a metric on building performance. And it's interesting because that's a cultural metric, right? Cultural economics, it's something that's human devised that we share collectively. We then moved on to energy as a metric, and it too is more of a cultural metric. It's very focused on the interaction between different systems and components, but once again, it's this accounting exercise of how we have interactions between different human entities. But carbon pollution is different. It's atmospheric pollution, and we're dumping greenhouse gases into the atmosphere. And in that way, it's not as much of a cultural aspect, it's a true like pollution metric. And our industry hasn't really been measuring it in regards to pollution to date. And it matters a lot because when you look at global climate commitments, if you look at business as usual versus different commitments, we've got this big gap right now. So you can see, based on global commitments, which are shown here, we've got, at the moment, we're closer to this 2.6 to 2.9 degrees Celsius threshold. And there's a big gap between kind of what people are doing versus what governments have committed to. And the only way we're going to get down to these commitment levels is to reduce the emissions or the atmospheric pollution into the atmosphere across the whole building sector. So the World Green Building Council put out a paper on this a few years ago, looking at it. And they noted, global greenhouse gas emissions, the building industry accounts for 39% of total emissions. So in 2018, they estimated that the embodied carbon portion of that was about 11%. So you can see it's about a quarter of the total of the building industry. But because the operational carbon emissions are cleaning up, they're estimating, when you look out to the future, it would probably be a roughly 20% as other portions of the world decarbonize. And embodied carbon is harder to decarbonize than operational carbon. And that's the reason for that. I was involved with Project Drawdown. It's a book that came out a few years ago. It was focused on helping solve the climate crisis and to look at it comprehensively with this idea of like, when can you actually start drawing greenhouse gases out of the atmosphere? So not only do we stop emitting, but we actually start to decline and reverse climate change. And one of the key ideas within Drawdown is this idea of sources and sinks. So back to this idea of atmospheric pollution, if the atmosphere, right now we have sources coming from electricity production, food and agriculture, industry, transportation, buildings, other energy-related emissions, right? And here you can see buildings is way smaller than that World Green Building Council number. And the reason is the way that Project Drawdown drew boundaries around the emissions was that it just looked at the buildings and not the electricity sector. Whereas like when the World Green Building Council or Architecture 2030 talked about roughly 40%, they include the energy that buildings consume from the electricity sector and a few other items. So that's how they get up to the higher numbers. So it always kind of depends on how you slice the pie. But the key concept here is that, you know, at the moment, we're overwhelming the sinks. So the natural sinks include land sinks, so that'd be sequestration through forests and soils, and then also ocean or coastal sinks. So roughly 60% staying in the atmosphere today. And when we look out to the future, there's this idea of, you know, not only drawdown, right, but how are we creating a circular economy? And one of the key ideas within the embodied carbon world is not just how you're reducing carbon today, but how do you keep that carbon from also having to go back through the system? Because if you look out 60 years, we don't really have much of a budget for additional emissions from construction. So, you know, to look at climate commitments, we need to be preparing for the future as well. And to create more of a closed loop on recycling and salvaging and keeping things from going to landfill so that there is more of a closed loop. So what is whole life carbon? So right now, you know, typical buildings will look at heat gains as a negative, stormwater as a negative, and there's carbon emissions as a negative. And when you start looking at metrics holistically, the goal is to start looking at these items as resources and how do you make the most of those natural resources that are on a site. And in that way, how can you get a project to mimic the ecosystem services that are present on the site? And it's amazing if you start thinking about that, you can actually measure that and quantify it and start to find ways to bring emissions down to zero operationally. And even within the embodied carbon sector, there's a lot of opportunities to bring emissions dramatically down. So cradle to grave is one of the first ideas that became pretty popular. William McDonough popularized that about 20-something years ago. Here you can see it's overlaid with the newer embodied carbon stages. So A, B, C, and D are associated with, so the A stages is your cradle to site. The B stages are your practical completion. So everything after that, including your operational energy, operational water emissions, maintenance, refrigerant emissions are all in the B stage. And then the end of life are the C stages. So it's C1 through C4. And I'll be using these quite a bit through other aspects of this presentation. So it's just really important to remember that A is cradle to site, B is after practical completion, and C is your end of life. The D stage are items that are beyond building life. It often comes into accounting items where there's some things that just don't fit neatly into the A, B, and C stages. So they kind of go into D, and there's different methodologies and debates on a number of portions of the D stages. When you look at this kind of combined, there's also inconsistency in the industry when people say the term embodied carbon versus whole life carbon. Often when people say embodied carbon, they just mean the A1 to A3 stages, which is the raw material supply, transportation, manufacturing. So it's essentially what are the emissions from making a device that goes into a building. But often, like when people say embodied carbon, it actually includes a lot more than that. It actually includes the A4, which is transportation to the site, the A5, which are emissions on the site. So any heavy equipment, fuel emissions would fall into that stage. It would include the B stages with churn and maintenance and refurbishment, and the end of life. The concept of whole life carbon is to look at it holistically. So to try to capture everything. So you've got, the upfront emissions from materials, you got the construction emissions, you've got the operational emissions from refrigerant leakage, you've got operational energy and operational water emissions, and all that falls into one number or a group of numbers that you can start comparing performance on. And globally, this is part of this vision per the World Green Building Council. There's a net zero carbon building commitment that all buildings within direct control to operate at net zero carbon by 2030. And that means that new buildings, infrastructure and renovations will have at least 40% less embodied carbon with a significant upfront carbon reduction by 2030. And then by 2050, new buildings, infrastructure renovations will have net zero embodied carbon, and all buildings, including existing buildings, must be net zero operational carbon. And it might sound like pretty feasible and doable for a lot of folks, but anybody who's kind of gone through these calculations, I think will tell you that to get to that 2050 vision is very challenging, and we're still figuring it out. So all of you are pioneers. We're really pioneers on this process right now, trying to figure out how do we solve this. And California is a pioneer with the regulations that Alper was talking about, as trying to build embodied carbon into the code is very new in the US and even globally. And we're going to have to be figuring out a number of things as we go with all of this. So why is whole life carbon important? One of the main reasons is trying to look at sinks. So once again, as an industry, traditionally, we looked at energy cost or energy use, which are both proxy metrics for carbon emissions. But even if we were measuring carbon emissions, we weren't necessarily looking at carbon sinks. So back to that drawdown diagram, we need to figure out both of them. And in an ideal world, buildings would be carbon sinks. If you build a new building, how could we create a concrete that's a carbon sink, or some other material that's actually sequestering carbon into the structure and materials of the building? Additionally, when you're looking at whole life carbon, you need to look at operational energy and emissions, and that includes time of use. So it's not just a static number, it's looking at interactions with the grid. How is the grid behaving? When are you pulling energy from the grid? What are the emissions associated with that? And accounting for that holistically. And then the churn within the building, when you're looking at reuse, repair, and recycling, and waste flows, all of that gets built into it as well. So that comes back to this whole life perspective. And the nice thing is when you do this, you can actually measure all these different things that traditionally had different ways of being measured and compare them across sectors to look at design options and design solutions to try to figure out which ones have the lowest impact. Something that we've been looking at within PAE is this idea of the A stages. So once again, that's the cradle to gate process, or cradle to site. And then the B stages, which are the operational emissions, getting to zero. And that's really important because the C stages, if I go back, that's end of life. So a lot of LCA or life cycle assessment studies, when they run the calculations, the end of life aspect of it can sometimes skew the math. in ways that might change decisions on a project. And there's much less certainty on the end of life of a building. And it is wise to look at that closely and make sure it's not necessarily changing decisions, because some of the assumptions might not be correct. And I'll get into that a little bit later on this presentation. Once again, when you're looking at A plus B, so if we could find a way to sequester carbon in those A stages. So how are we sequestering carbon in the actual construction of the building? And in the B stages, also, is there a way to sequester carbon? In this diagram, it's showing A is negative and B is positive. B can also be negative if you're exporting energy to the grid annually and helping decarbonize the broader electricity network. There's a case for that. So trying to look at both of these in balance to come up with a way to get to zero. This is from a project we worked on, illustrating, some examples of this. So with this project, we were looking at wood construction. There's a lot of interest in biogenic carbon in the industry right now and the benefits of that. This is showing that as a negative value, so you can see it being sequestered here. We also have emissions from architectural and structural, interiors, MEP, and TI. This is much newer. For a lot of projects, they haven't looked at MEP emissions. We've been doing this for quite a while now, and it's fascinating. As the MEP 2040 commitments come out, there's a lot more interest in the embodied carbon of MEP systems, and something that we found is that they can actually be quite a bit higher on projects as project TI and churn gets accounted for. So that can change it quite a bit. On this project, it also had the B stage emissions, operational emissions, and then deconstruction and the D aspect. Now, the interesting thing is when you look at net zero, there's a lot of different definitions of net zero out there. So on any project we're on, we're always asking net zero what? So, California has its own definition, DOE has its own definition, LEED has its own definition, ILFI has its own definition. And it makes for a lot of confusion because there isn't a consistent metric for zero. Even the federal government just came out with a newer metric on that. And here I'll just kind of demonstrate that. So this is looking at, okay, if you had your architectural and structural construction, looking at the biogenic carbon sink and carbon offsets. So trying to get to zero with just the architecture and structural. So a lot of third-party certifications look at net zero in this way at the moment. When you build in the interiors, MEP, and TI, it changes. So all of a sudden you need, additional offsets or additional sequestration on site to balance that out. And then if you add in, refrigerants and maintenance, there's a whole nother chunk of that which hasn't been accounted for. And then operational emissions adds for a whole nother section. So right now on a lot of projects, there's a lot of missing carbon emissions or carbon pollution that's not being accounted for holistically. And then one of the main goals of whole life carbon is to make sure you're looking at it all across all sectors. When it gets to offsets, this is something that's quite controversial sometimes. There's a lot of moving pieces and discussions. I guess the main comment here is make sure if you are going to use offsets, different third-party certifications to make sure that they're high quality offsets. ILFI has some good guidelines on that for any of their programs. So I'd say that's a good benchmark to start with. So when should this be implemented on projects? So we would recommend looking at it early. So here you can see this green dynamic line. ideally, there's initial assessments on trying to look at whole life carbon. And the reason to do that is the sooner you measure concepts, the sooner you'll understand the impact. There's a quote, you know, if you're not measuring where you want to go, you're going to end up somewhere else. And that's exactly it. You need to start measuring where you want to go early. Set the vision for when you go and start measuring that to make sure you're on the right path. So how can your projects implement this? First off, this is another example from a project looking at all the stages, so A through D. And one thing we've been doing quite a bit are these dashed lines looking at confidence in the data. So one of the challenges with embodied carbon is there can be data quality challenges. So when you get into the details of an LCA, you might not be able to find an EPD on a certain material, or the actual estimated emissions is like a proxy EPD or from some benchmark study for other LCAs. And all of that means that sometimes things can be a bit off from what ends up in the project. And you have to be careful not to get lost in the minutia. If you start worrying too much about the embodied carbon of every tiny widget, you can get lost in minutia and it's not necessarily beneficial. You need to look at like the big ticket items and how do you reduce those, and then keep going down the line and try to get as far as you can. Eventually, as noted in that World Green Building Council goal, we need to try to get everything to zero. But at the moment, the architectural enclosure industry is ahead of a lot of other aspects of it. A lot of the interiors manufacturers have jumped on board with this, and the structural materials are definitely quite advanced. When you get into MEP and technology, once again, we're pioneers. It's very new. It's hard to get high quality EPD data. And there's often a lot of estimates and proxy data that has to be used. So it's good to show that level of confidence. I have a pet peeve with projects where they show the overall carbon emissions to like 3 decimal points, because in reality, you know, it's plus or minus a decent percentage based on the data quality. This is just another way to look at that. So looking at the stages and this kind of level of confidence across the board. I guess one other thing to note is on the operational emissions, this is just noting, you know, we have much higher confidence in estimating operational emissions based on years of energy modeling and being able to track projects. We can be quite confident that we'll be within a small range of performance as long as we get the right inputs on the owner side, but embodied carbon can be quite a bit different. So this is from a project in Washington State. We were looking at the A1 to A3 emissions, and this is another way to try to look at it as a source and sink. So in this example, you can see the sources with metal, miscellaneous concrete, MEP, and insulation, and the sink acting as sequestration once again with wood construction accounted for, and a little bit in the landscape. The operational emissions, another aspect of it, in addition to the hourly emissions factors, there's another level of complexity in that the future projections of the grid change. And it depends on which projection you want to use when you're running your calculations. So in this example in Washington State, we were looking at the 2018 Washington State Energy Code. So this is this 0.7 number. PSC data, that's the utility up here on the project that we're working on, had this line. And then we had PSC projections and then a CETA compliant projection based on the regulatory environment. So the utilities are definitely cleaning up the grid exactly when they can get to zero is not clear. There's the regulatory targets, but a lot of the utilities are still struggling to figure out how to get that low as well. So once again, it's kind of like when you look to the future, it's nice to have scenarios and you can test the scenarios and have the conversation with a client. This is looking at a 60-year time frame, so 60-year operational missions. For a typical LCA, that's the time frame that's used. That's for ISO standards. I'll get into that a little bit later. So this study uses 60 years. But one of the things that can happen with that is you may have an overemphasis on one aspect of the study or another based on the timeline. So here you can see the operational emissions keep growing over time. The refrigerant emissions as well. So this is a air source heat pump solution. The refrigerant emissions are actually relatively small compared to a lot of mechanical solutions, like VRF can have really high refrigerant leakage. But because the grid's already pretty clean, the refrigerants can start to matter more. Similarly, on the embodied carbon, you start out with this big emission source up front, and then it grows. This is each TI assumption and equipment replacement, and that bumps up the cumulative aspect of it. So you can see if you just look at operations, the overall emissions are, in this example, roughly 1,200 metric tons. But when you include embodied carbon, upkeep, which is churn, and refrigerants, it's almost 5,000. So you can see why like whole life carbon matters a lot, because if you just looked at operational emissions, you're missing a huge chunk of the overall emissions on the project. That A plus B target that I noted before, this is trying to look at, okay, if you were to get A plus B to 0 in 15 years, and that's looking at climate commitments to say, let's get to net zero carbon, by 2040, that this would be the kind of rough estimate. And you can see, even with sequestration, so once again, this is another wood project. It's able to sequester some through the construction process, but there's still this big chunk of offsets required in addition to offsite renewables and onsite renewables. The next project's the Rocky Mountain Institute Innovation Center. This is in Basalt, Colorado. It's a project that we worked on a number of years ago. It's a unique project. It's achieved all kinds of certifications. And we looked at this from a whole life carbon perspective after the fact to kind of see like how long does it take for it to hit net zero carbon. And it's a fascinating study because this project's net positive. It generates about 200% of the energy that it uses. It has almost no refrigerants. It's a passive solar design. So the glazing here, it's a quad pane glass. It has active solar control. It's climate responsive by orientation. So each orientation has its own unique aspects. It's a passive house project, and it has passive cooling. So it's very, very passive. We started. This is the first project that we started where Amory Lovins asked us to not put mechanical systems in it. It's like, can you design a building without mechanical systems and have it be fully passive? And it was an interesting process because we were able to go through by getting the architecture to perform well enough. We were able to keep taking out mechanical systems to really simplify it to the point where we just had simple electric heat in the floors and passive cooling, and that's how we help get rid of the refrigerants. It also has wood construction, so there is some sequestration in that aspect of it. But even with all that, which is like great, right? From a whole life carbon perspective, we found it still takes about 16 years for this project being net positive to offset itself. And that's without carbon offsets, to just kind of say, like, if it's generating more energy than it uses, how much is it benefiting the overall region? And that was also kind of a wake-up call for me, where it's like, even here, this kind of very sustainable thought-leading project took about 16 years to hit zero. So here you can see that embodied carbon, the net positive drawdown. This is a blip on some refrigerant leakage assumptions, and then down to net zero. The next project's the Bush School. This is in Seattle, Washington. It's a historic renovation of this Gracemont building. And here we're looking at a number of different metrics. Traditionally, when you're looking at insulation and structure and rigid insulation, EUI, refrigerant canisters, all of this, there was no way to bring it all together and compare it outside of cost. Like, what's the energy use of a can of refrigerant, right? What's the energy use of spray foam? There isn't really a way to track that. But when you look at it in terms of carbon pollution to the atmosphere, you can actually measure each one of them and start to have an iterative process to understand design options. So here you can see we were looking at, because it's a renovation project, one of the defaults for historic renovation in the Northwest is a VRF mechanical solution. That's variable refrigerant flow. With those systems, if you're not familiar with it, there's an exterior condensing unit that uses refrigerant to move heating and cooling through a building to indoor units. And with that, there's a lot of site-built refrigerant lines. And site-built refrigerant lines are prone to much higher levels of leakage than systems built in factories. And due to that, refrigerant leakage can become a much bigger impact. So here, with a new code-compliant building, so we're just kind of assuming we bring that historic envelope up to the Seattle Energy Code, which is quite stringent. You can see the structural seismic upgrades are accounted for. We've got interior finish upgrades here. And then you can see the refrigerant emissions are quite high on this. And then we've got operational emissions. This is really low because in Seattle, our utility emissions are extremely low. So another thing that happens when you're looking at whole life carbon, the numbers can shift around a lot, and they're highly local and highly regional. So just because you're used to a rule of thumb in California or Washington, it doesn't mean you should apply it to Wyoming or Massachusetts or New York. It's going to change a lot more than energy metrics will. The next option is renovation of with minimum spray foam and a VRF system. So once again, you can see, like, by reducing the amount of spray foam, it helped quite a bit because the spray foam is kind of baked into this one. Renovation 2 had increased spray foam and the air to water heat pump. So here you can see the increased emissions from the spray foam and the reduced emissions on refrigerants, because the air to water heat pump is a package system that's built in a factory, and that helps reduce the overall refrigerant leakage rates. The next option was a minimum spray foam. Oh, that's a typo, sorry, with an air to water heat pump again. And then the last one is a polyiso board, so avoiding the spray foam and air to water heat pump. And you can see from an emission standpoint, this one has roughly 300 metric tons of CO2, whereas, you know, the original code compliant one had almost 1,100. The wild thing is, if you looked at these two from an energy perspective, they're almost identical, almost the same EUI. But from an emission standpoint, you know, this one's a fraction of where you start. And it's another reason to, when you look at carbon pollution, you'll come up with very different outcomes than just energies. So the next one, this is projects up in the Seattle area that we've been working on. Here, it was interesting. We were looking at, once again, a wood construction option. And this is looking at the positives or positive emissions into the atmosphere. The negatives looking at sequestration, and this is the balance. The wild thing here is the below grade parking garage on this development was the largest source of emissions. And there's been some research on this recently. Some others have been showing just how high that is. And for a lot of cities, when it's mandated under the zoning, the emissions from parking vehicles can be quite extreme. And especially when it's all below grade, one of the biggest carbon saving measures on this project was reducing the number of parking spots and just how much was being excavated, which was fascinating. So once again, when you look at carbon pollution and you start measuring it directly, it can just make you ask questions that maybe you've never asked before and change design decisions in fascinating ways. This is another one of these charts that from A, B, and C stages, just kind of looking at that and the confidence of it. Already touched on that, so I won't dwell on it too much. The next one is UW Founders Hall. This is one that we worked on with LMN architecture. It's a mass timber structure and has a number of interesting design features, including being fossil fuel free. It's interior rendering of it. And one of the lessons learned from it, we looked at emissions with LMN closely on over 100 years, trying to understand, you know, how does this progress? And one of the things that we found was with the churn, if you expand the timeline from 60 years to 100 years, the structure starts to matter less. It's still really important up front, but over time, interiors and MEP systems start to matter a lot more, just because those are the parts that are replaced more often. And this is just a great example of when you change parameters of a scenario, you can come up with different outcomes. So you need to look at it holistically. On this example, when we were looking at it from a LEED perspective, the LEED whole building LCA accounted for about 33% of the emissions. And the unexplored carbon here you can see included landscape, MEP, refrigerants, operation energy use, and interiors, which is about 67% of the overall emissions over 60 years. So once again, depending on the rating system or third-party certification, they're measuring different things, and it's good to understand what they're including and what they're not. This is looking at that uncertainty again over 60 years, trying to understand impact of each of these stages. So, question, do you believe the 60-year building lifespan in LCA studies accurately reflects our climate goals? Does anybody want to comment on that?
Also, you could respond via chat if that's easier.
Yeah, no pressure. It's you know, late on a Tuesday. Well, for us, we believe that it's pretty questionable. It is the international standard. It comes from ISO. I think it probably was set based on the average lifespan of buildings globally. But often, for any projects architects are involved with, or anybody on this call, like for the most part, buildings that you're going to work on are probably going to last a lot longer than 60 years. And it's interesting if you start thinking about it, like, well, how long should a building last? So I'm in the Bullitt Center right now. This is where our office is in Seattle. And it was designed with this idea of a 250-year lifespan. It's the first project that I ever helped work on that has this idea of a 250-year lifespan. And it changes things a little bit. So this one has this category 2 structural performance. It has passive design, daylight, heat, cooling, net positive energy, net zero, net positive water. Imagine most people on the call have probably at least heard of it. But one of the things is, if you look at a typical LCA, if you were to assume 60-year lifespan, that means in 250 years on the site, as a society, we'd be building 5 buildings, which is a pretty strange assumption to start with if we're trying to solve the climate crisis. We don't have the emissions to kind of spare when you look out that far. So when you start thinking on a longer time horizon, it just changes some of the questions and assumptions, and some components can start to matter more, and it helps think about longevity and durability as well. PA Living Building, this is another project we worked on. It's recently completed. It's in Portland, Oregon. It's also a living building project. And this one had this idea of long-term materials and generational usefulness. One of the aspects of that is looking at making it a category 4 structural system. So this project's gotten more attention in regards to the living building status, but the structural aspect's quite fascinating. It wasn't that much of a premium to get it to category 4 structural performance. And with that, it means that it has similar performance to hospitals and fire stations. And we don't have that many buildings that are designed to that. But it was designed to last 500 years, was the concept. And once again, if you're going to think about a building lasting 500 years, it's pretty hard to justify not having it be category 4 structural. It does have passive design features, it has a full microgrid and nutrient recovery system as well. But once again, if you just look at kind of simple math of it, it's fascinating. In 500 years, there'd be 9 buildings here based on a typical LCA. So one of the main concepts is to just like rethink that, so that when you look at a longer time horizon, not letting the end of life aspects dominate it too much. And I'll kind of show you why, because often end of life, if you've got a wood project, for instance, the way that an LCA accounting process works in the US is you might be able to take credit for the sequestration of the wood materials in the A stages. But then at end of life, it's assumed that they'll probably go to landfill and go back to the atmosphere. So the benefits of wood, or if you want to use other natural materials like straw or hemp or newer biogenic sources like that, at year 60, it means it's going back to atmosphere. So then it starts to neutralize that sequestration benefit. And an interesting question is, if you could show that the building's designed to last much longer, can it have more of a long-term sequestration potential? And it's worth having that conversation. In the regulatory environment, all of this is still, very new. As I mentioned, we're pioneers. There's a lot of territory to be worked out, but I do think when you look out 10 years from now, if all of us could like go 10 years in the future and have this exact same call, we'll probably live in a building industry that has a carbon code, not so much energy code, and we'll be looking at way more solutions from a whole life carbon perspective, because we have to actually hit these climate commitment goals. And with that, I think we're at 1 hour. So kind of stop there, and I guess I'll open up the chat and see what other people have. Does anybody have a question before we kind of look at the chat?
Hi, this is Pamela here. And how are you dealing with building for deconstruction and then deconstruction back to recycling without having a lot of logistics just deter the entire benefit of trying to recycle product?
Yeah, I mean, that's one of the it's kind of, I mean, there's so many challenges when you start looking at it from a whole life perspective, right? I didn't touch on that as much. I mean, that goes back to the circular economy idea. So back up at the top, we have a lot of work to get to this point. The salvage market has grown some. Different parts of the US have more of that than others, but I know some practitioners in the LCA world who struggle to see how we can hit some of these climate commitments without large-scale salvaging of materials. And at the moment, there's a lot of waste in the building industry, and that's something that we're not seeing as much. So I think there's a lot of innovation opportunity to try to figure out how to make that pencil. I think one of the challenges is cost. I've been on a lot of projects over my career where you'll look at saving a building versus tearing it down and building new, and the cost of saving it or repurposing things is higher than building it new, and it's largely labor driven. And that's a big challenge. And we need to figure out how to price it correctly and help make it happen more often.
Agreed. Thank you.
So I had a question.
Yep.
You do a lot of different kinds of buildings, and I was wondering if you could talk a little bit about how you've been addressing the commercial buildings, because it's obvious that the institutional clients are more willing to consider all these factors than, say, some retail developer or maybe even residential developer. How do you approach those clients?
Yeah, that's a great question. The best example we have of that is our PA living building. So go back down to that quick. I don't have the financials here, but this was a developer-driven project. So our Portland office is the main tenant, but this had to meet the pro forma of a development. And it's interesting. Paul Schwer, our president emeritus, has a brilliant presentation on this where he can speak to developers to help them understand the capital stack and how the financing of the whole process worked. But there's some fundamental assumptions in the development process where if you shift them around a little bit, you can find the value of green buildings in ways that they may not be used to. The tricky part is to make sure there's an opportunity to have those conversations with developers and to make the case for it. I mean, not all developers are going to go for it by any means, but I have seen I mean, there is a lot of innovation happening in the development community still, and there's interest in it because there's often developers can get higher revenue streams with a green building. Had one developer years ago ask how to create the green vibe because they see lower, they have better retention and they higher revenues for their green buildings, but it's often it's hard for them to quantify exactly what that is that translates into it. But I think for everybody, like, it's kind of up to us to educate and help show what's possible and hopefully get people moving in that direction.
Just one more thing. In Hawaii, some of the land trusts, like the Queen Liliuokalani Land Trust, have a mission of building for many generations and educating the Hawaiian tradition. And so they use 300 years as their model for what they're building for. I was wondering if you've done any work in Hawaii or any group for land trusts, either Alaska or Hawaii, where they think that way.
I have not personally. I mean, that's great to hear. I've worked a little bit on some tribal work, and it's great. That perspective helps a lot, right? Because then it just changes the conversation and helps people think longer term. But I mean, it's still rare. I gave this presentation at Greenbuild, and I had a woman come up from a federal department and say she wished she could have 30 years or 60 years, like often federal LCAs, something like 15 years or something shockingly short, where the time frame is just this really short period. So it just skews things a lot. I guess I'm not sure with the chat, how should we be answering questions in the chat? We technically have time, or do people who put them in the chat want to ask any from AIA's perspective? Is there rules on that or no?
I think if you're finished with the presentation, it's anything goes at this point, but this is Pamela again, and in full disclosure, I'm actually with Rockwool. So my question, I was just a little surprised to see so much foam products in your projects that you were discussing, considering the sustainability issues, the combustibility, and the off-gassing and things of that nature. What drove that? Was that a cost factor in most cases?
Oh, foam, yeah. Well, spray foam, the historic renovation, right? Like that, spray foam often comes up. The blowing agents, they're trying to show how to avoid that. I mean, polyiso's, better. That XPS was really bad. It's nice with the newer regulations on XPS. So,
Yeah.
that's helped a lot. But yeah, I mean, it's the reason to do whole life carbon, so you understand, because like a passive house is a great example where you could have a passive house project that's super insulated, super low energy, but say it used just like boatloads of spray foam. The overall emissions of the project could be really high, but people aren't measuring it. So then you don't understand that impact correctly.
Thank you.
Yep. Well, I'll just go through a few questions. Jason, I see your question. I'll just read out loud. So when making the decision to build 250 or 500-year building, are future advancements and innovations and materials considered? For example, maybe in 100 years, there'll be new materials that sequester more carbon and are more recyclable than today's materials. Yeah, I think that's absolutely right. I'm sure there will be. How you build that in, I think it'd be a scenario that, a project could run estimates on. There's a lot of innovation to be done here. So if anybody has some brilliant idea help solve that on the material side. We need more products that can sequester carbon or drastically reduce carbon. So yeah, that's great. See, Frank Fuller said 100 years is better. Yep, I agree. I think a couple time frames is helpful so you get a different sense of it. And then one more, how was your experience with MEP and whole life LCA or whole life carbon studies? Yeah, we've been doing a bunch of MEP work. First one I did was 7 years ago on OSU Forest Science. It was a project with Michael Green's office. We had to do a lot of hand takeoffs on the MEP and come up with our own estimates. It still tends to be pretty manual. You can't just like pull numbers out of Revit or anything like that easily. So the MEP 2040 commitment is going to help standardize it more, I think, as more and more MEP firms are doing these calculations. But right now, it's still, we're pioneers. And I think collectively as an industry, we're figuring it out as we go. So, yeah. I think those are all the questions. So
I was just going to add one more comment. Getting back to the commercial side of things, it's now for banks to loan money on a lot of commercial projects, they use a 99-year ground lease. And that's actually true for institutions that own land and want to build on that land. It might be that it could be the what's built on those ground leases could follow more in the timeframes that we're trying to talk about for carbon sequestration.
yeah, that's great.
Just a comment.
Yeah, that's interesting.
Well, gentlemen, thank you so much for your presentation and for that broadening of perspective. I think sometimes when you have your nose to the grindstone, it can be easy to lose sight of those more far-reaching and far-ranging goals. And just having that outline in front of us, I'm sure all of us are scrambling to think of ways that we can make it happen today. So again, thank you very much. And thank you to PAE for a really excellent series of lectures over the course of the past year. Really four of the best lectures I've attended this year. And so please accept our thanks and look forward to hearing more in the future.
Yeah, thank you very much. Thanks everybody for your time.
Thank you.
Yeah, thank you. Our pleasure.
Thank you very much.
Thank you.